Once again, welcome to Mathematics Solution. And today we want to look at hyperbolic functions. By the end of this lesson, by the end of hyperbolic function topic, you should be able to define and state applications of hyperbolic functions. Also, should be able to state the properties. State the properties of hyperbolic functions. Also be able to draw the graphs of hyperbolic functions. And finally, be able to solve. Before we solve, we should be able to prove hyperbolic identities. Then we should be able also to solve equations involving hyperbolic functions. So let us start. We can start on definitions. So what is hyperbolic function? So an hyperbolic function are functions associated with the geometry of the conic section and these conic sections are called which are called hyperbola. So the functions which are associated with this geometry are what we call the hyperbolic function. Now, hyperbolic function is widely applied in various fields. Among them being, so you can say that hyperbolic functions and get out of that. Hyperbolic functions are used in various fields. Among being engineering and in real world hyperbolic function, and in real world hyperbolic functions are used to model they are used to model the shape of suspension bridges, also calculating the trajectory of projectile Hyperbolic functions can also be used to describe hyperbolic functions can also be used to describe the spread of heat, describe the spread of heat in a solid. So that is the introductory part of hyperbolic function. Now I want to understand mathematically how to define hyperbolic function. Mathematically can have hyperbolic function hyperbolic functions mathematically are defined as follows. So number one, we have hyperbolic sine of x. So I can say, okay, hyperbolic sine of x written as sine hyperbolic of x is equals to exponential x minus exponential negative x all over 2. And in short, it can be written as sh of x to be equal to exponential x minus exponential negative x, and this over 2. So we read sh as shine. So read as shine of x. You can read it as shine of x. Then number two, we have hyperbolic cosine cosine of x, we write as cosh of x, which is equals to exponential x plus exponential negative x all over 2. And in short, you can write as ch of x, which is equals to exponential x plus exponential negative x all over 2. So this one is read as cosh. It is read as cosh, the cosh of x. It's read as cosh of x. Now, to get the hyperbolic function or the hyperbolic tan of x, we are going to apply the same principle that you applied in trigonometry. That is, now let us go to number 3, hyperbolic tangent of x. You can say that it is written as the tan hyperbolic of x is given by the sine hyperbolic of x over the cos hyperbolic of x. So, and in short, the tan hyperbolic of x is written as th of x is equals to the sine hyperbolic of x. We have said it is exponential x minus exponential negative x all over 2. We divide by the cos hyperbolic of x, which is exponential x plus exponential negative x all over 2. So we can change the sign and get the reciprocal, so that you can say that th of x is equals to exponential x minus exponential negative x over 2 over exponential x plus exponential negative x. And with that, we read this as, is read as tan. So it is tan of x. So the th or the tan hyperbolic, you can read as tan of x. So from there now you can have the special cases, that is the reciprocals of these hyperbolic functions. And so you can go to number 4. And number 4, you can have hyperbolic cosecant of x. Hyperbolic cosecant of x. So you write as cosec hyperbolic of x. As we know, in trigonometry, we had said, let me just put you a reminder here. Remember this one. Remember, cosec of theta is equals to 1 over sine theta. Sec of theta was equals to 1 over cos theta. And then cot of theta was equals to 1 over tan theta. So this is in trigonometry. This implies that there is a close relation between trigonometric functions and hyperbolic functions. But today you're not going to look at the relationship between the two, the hyperbolic functions and the hyperbolic functions, but we shall look at it maybe in another lesson. So this implies now for the cosec hyperbolic function, it's still going to take the same meaning to be equal to 1 over the sine hyperbolic of x. So this means it's only the reciprocal. And so you can have it as the cosec hyperbolic of x is equals to 2 over the exponential x minus exponential negative x. Then number 5, we have the hyperbolic secant of x. So we write this as the sec hyperbolic of x is equals to 1 over cos hyperbolic of x. Now, for this one here, we read as cosec, or maybe you pronounce as cosec. So you can say the cosec of x. That would mean the cosecant hyperbolic of x. Then this one here, we are going to have the sec hyperbolic of x is equals to 2 over exponential x plus exponential negative x. So we pronounce this as sec, the sec of x. We pronounce it as the sec of x. Now, so number 6, we have the hyperbolic cotangent of x, and this one we have it as cot. The cot x, and this will be implying 1 over tan hyperbolic of x. So this implies we're going to have the cot of x as being equal to the reciprocal of tan hyperbolic of x, which is exponential x plus exponential negative x, all over exponential x minus exponential negative x. So we read this one as the cot, or pronounced as cot. If we go a little bit back, I think there was another one that we put it like that. It's not so it is cosh, not cot. So we are okay, we are correct. So the next step that we need to go and check, we want to check on the properties of these hyperbolic functions. What are the properties of these hyperbolic functions? What are the properties of these hyperbolic functions? So we go to properties of hyperbolic functions. Now, the first one, we want to check what is sine hyperbolic of 0. So number 1, let's check the sine. So let f of x be equal to sine hyperbolic of x. Find or evaluate f at 0. So in this, we're going to have solution. So how have we defined our SH of x? So we have defined it as SH of x is equals to exponential x minus exponential negative x all over 2. So this implies that our f of x is equals to exponential x minus exponential negative x over 2. So this basically tells us that if I want f at any value here, I just replace the x with that value. And in this case, I want f at 0. So it means that in this expression, I'm going to do what? I'm going to substitute the x with 0 so that I'm going to have exponential 0 minus exponential negative 0 and this over 2. So you need to remember from indices that any number raised to power 0 is equals to 1. So if you can remember that, then that implies that exponential raised to power 0 is also equal to 1. And exponential raised to power negative 0 is also equal to 1, because negative 0 simply means it's negative 1 times 0. And that will become 1. So that it means we are going to have our f at 0 is equals to 1 minus 1 over 2. And this is equals to what? And this is equals to 0 over 2. So this simply means that our f at 0, which is equals to sine hyperbolic at 0, is equals to 0. So suppose maybe it is the cos hyperbolic of x. Case number 2, maybe if you can have, let f of x be equal to the cos hyperbolic of x. Evaluate f at 0. So how do we do this? We follow the same steps. You start by defining the CH of x. How we define the CH of x? We have said CH of x is equals to exponential x plus exponential negative x over 2. So this simply means now our f of x will be equal to exponential x plus exponential negative x over 2. Now, again, you want to evaluate our function at 0. So this means we are going to have f at 0 will be equal to exponential 0 plus exponential negative 0 and all these over 2. So again, you can remember that any number raised to power 0 will be equal to 1. And so we're going to have f at 0 is equals to 1 plus 1 over 2, which is equals to 2 over 2. This implies that our f at 0, which is equals to ch at 0, will be equal to 1. Now, if you can remember also again, if you can go back to trigonometry. In trigonometry, sine 0 is equals to 0. Cos 0 is equals to what? To 1. And tan 0 will be equal to sine 0 over cos 0, which is equals to 0. So it means that there's still a kind of a relation between trigonometry and hyperbolic. But that we will not look at it today. But we shall look at it maybe in another lesson. Thank you. Now, let us look at the other property. We have just seen in this property that the sine of 0 and the cos of 0, they still correspond with what we obtain in trigonometry. That the sine of 0 is equal to 0, and you can see that the sine hyperbolic of 0 is also equal to 0. The cos of 0 is equal to 1, and the cos hyperbolic of 0 is also equal to 1. Let us look at now in terms of the type of a function, whether it is an even function or an odd function. So we go. So we want to check on the even function and the odd function. So we can start with the odd function. Now, what's an odd function? So you say that a function f of x function f of x is said to be an odd function, is said to be an odd function if f at negative x is equals to negative f of x. So we want to see how do we prove such a property. How do we prove that such a property? So we want to check with the sign hyperbolic of function. Now, before we go with that, let us just evaluate a simpler function here. What do we mean by having f at negative x and f and negative f of x? Suppose we have maybe f of x is equals to maybe x cubic, right? So f at a, if you evaluate this function, f at a, it will be equal to a cubic. That is, wherever there is x, we substitute with the value in the bracket. That is what we call to evaluate a function at any given point or any given value. Now, if we want to check what will be f at negative x, it simply means wherever I have x, I put negative x. So it will be negative x and all of it cubic, right? And so if you check this one here, it is the same as this one is the same as negative 1 times x, then cubic. If we go to indices, in indices, we shall say that now we have f at negative x being equal to negative 1 cubic times x cubic. So that negative 1 cubic is negative 1 because it is negative 1 times negative 1 times negative 1. You'll get is equals to negative 1. So f at negative x is equals to negative 1 times x cubic. So you get that this one, f at negative x is equals to negative x cubic. But this x cubic is our f of x. So you can have it as f at negative x being equal to negative f of x. And this tells you that hence f at x being equal to x cubic is an odd function because it has satisfied the axiom or the property that f at negative x is equals to negative f of x. Now, in relation now to hyperbolic functions, let us look at the sign hyperbolic of x. The sign hyperbolic of x. Suppose f of x is equals to sign hyperbolic of x. Determine whether it's an odd function. determine whether it's an odd function. So what do we do on the solution? We come to solution. In the solution first, we need to remember, what do we mean by odd function? An odd function must satisfy the property f at negative x is equals to negative f of x. And here we have to define now our f of x. We have our f of x as being equal to sh of x. From the definition of sh of x, we say that f of x is equals to exponential x minus exponential negative x, and this over 2. Now, with that, you can now check, or maybe you can evaluate f at negative x. So f at negative x will be equal to, wherever there is x here, we shall substitute with negative x. So this negative x, it will be negative into bracket negative x. So we're going to have exponential negative x minus exponential negative x, and this over 2. So with that, we can have f of negative x is equals to exponential negative x minus this negative multiplied by this negative will become positive. And so you're going to have exponential x over 2. A reminder, if you have a minus b, I can factorize it the same as to put a negative outside, and you have b minus a. Because if I open up the bracket with this negative times b to become negative b, and negative it will become positive a. Right? So from that case, we want us to factorize this negative outside so that you can have f at negative x is equals to negative into bracket exponential x minus exponential negative x, and over 2. Remember, the sign has only affected the numerator, not the denominator. So this implies that, so we'll need this, we'll have this one as our f of x, negative x, is equals to negative. If you check whatever we have here in the bracket, exponential x minus exponential negative x over 2, it is simply the sign. It is simply the sign hyperbolic of x, of which the sign hyperbolic of x is our f of x. So you have f of negative x is equals to negative f of x. Hence f of x being equal to sh of x is an odd function. Is an odd function. So let us look at an even function. Even function. So you see that for the even function, we see that a function f of x is said to be an even function say to be an even function if f of x if f of x is equals to f of negative x. If f of x is equals to f of x, like that. So, example. So suppose f of x is equals to ch of x. Determine whether it's an even function. It's an even function. So let us do the solution for this. The solution. So again, we said we have to define the function as is supposed. So we have our f of x being equal to the ch of x. And we say that ch of x is defined as, so f of x is equals to exponential x plus exponential negative x over 2. So for the question, we have to show that f of negative x is equals to f of x, like that. And now this one tells us what? F at negative x will be equal to what? If you evaluate this function at negative x, then whenever there is an x in the function of x, you're going to substitute with negative x so that you have exponential negative x plus exponential negative into bracket negative x, and this is over 2. In the denominator, I don't have an x, and that is why it's not affected by the way we are evaluating. So we're going to have f at negative x is equals to exponential negative x plus exponential x over 2. So addition is associative, and so it means that a plus b is still the same as b plus a, right? And so with that, it means in the numerator, we can still interchange our two parts of the function. So we have f at negative x will be equal to exponential x plus exponential negative x over 2. And the reason why we're interchanging is so that it can look similar to the definitions of the hyperbolic functions that you already have. And you can look at your right-hand side, the function is similar to the cos hyperbolic. And so you can say this is f at negative x is equals to cos hyperbolic of x, which from the question, we have defined it as our f of x. So f at negative x is equals to f of x. So we conclude and we say that, hence, f of x is equals to ch of x is an even function. Is an even function. So those are the two properties. Now, let us see, how do you evaluate an hyperbolic function? To evaluate an hyperbolic function. To evaluate an hyperbolic function using calculator. So how do we evaluate an hyperbolic function using a calculator? So we have different types of calculators. We have the FX. We have the FX 570 ES plus, like this one. And we have the other one, FX 100, which is commonly used by most of the college students. And we want to see how do we evaluate. So what we do, you can write a small procedure on how we evaluate using a calculator. So procedure. So procedure. So you switch on your calculator first. Switch on the calculator. Switch on the calculator. Then press Hype button. Press Hype button. The Hype button, it is just below the X squared. If you can see the Hype button here, it is here. See here, this is the Hype button here. So that's the Hype button. So after pressing the Hype button, you press the shift. So if I press Hype button to this calculator, when I press the Hype button, I'll get the hyperbolic functions. But now with the FX 100, it is not direct like that. So you will press the Hype button, then press sign button to have sine hyperbolic or cosine to have cos hyperbolic, or with tan to have the tan hyperbolic, right? Then you put now the value. In the value. In the value and press equal sign. Let's do an example. Evaluate the sine hyperbolic of 5.4. So solution. So what do? We go to our calculator. You press Hype. So when you press Hype, what do you get? Hey, after pressing Hype, you press Hype sign. What do you get? Thank you. So you get sine hyperbolic. So after you get the sine hyperbolic, you press 5.4, and then you give the answer. What do you get? So the sine hyperbolic of 5.4 is equals to what? You get a value of 110, 110.701. Alternatively, you can say that the sine hyperbolic of x is given by exponential x minus exponential negative x over 2. So this implies now the sine hyperbolic of 5.4 can be given as exponential 5.4 minus exponential negative 5.4 over 2. You'll still get the same answer as 110.701. So we now want to look at the graphs of hyperbolic functions. Graphs of hyperbolic functions. The graphs of hyperbolic functions. Now, we can say that the graphs of hyperbolic functions, they can be plotted using a calculator. So we can say, for instance, so let me just put down the note. Hyperbolic function graphs, the hyperbolic graphs. Hyperbolic function graphs can be plotted using the calculator. And when we mean by using a calculator, it means that we are using the calculator to obtain the values of the dependent variables. Now, for instance, given the value of x to be between negative 3, and positive 3. Draw the graphs. Draw the graphs of y1 is equals to sine hyperbolic of x, y2 is equals to cos hyperbolic of x, y3 is equals to tan hyperbolic of x, y4 is equals to cosec hyperbolic of x, y5 is equals to sec hyperbolic of x, sec hyperbolic of x, then y6 is equals to cot hyperbolic of x. So solution to this graph, I'm going to draw using a GeoGraph. So I'll use GeoGraph to have a perfect draw, but already you're supposed to have a table when you can have this table, but then drawing you're going to have, so solution, we have x, and this x is running from -3, -2, -1, 0, 1, 2, and 3. So then you have now y1, which is equals to sh of x. So the values for that keying the values. Negative 10.02, 10.02, negative 3.63, then it's negative 1, negative 1.18. Sine hyperbolic of 0 is 0. Then you have 1.18. and 10.02. Then we have y2, which is equals to ch of x. For the ch of x, we have 10.07, 10.07, 3.76, 3.76, and then 1.54. Then you have 1. I'm going to have 1.54, 3.76, and 10.07. Then you have y3 is equals to th of x. By th of x, you have negative 0.995. And remember, th of x is equals to sine sh of shx over chx. So then the other it will be negative 0.97, negative 0.97. Then you have negative 0.77, 77. This one will be equal to 0. It will be equal to 0, and then the other one is going to be equal to 0.77. 0.77. This one will become 0.97 and 0.995. So for the code, for the code and others, we're just going to have the similar, but let us just have a plot of these 3 graphs in the GeoGebra. So I just go to GeoGebra. Let me see how they look like. But even before you go there, you can have a sketch. Let us just have a sketch. You can have a sketch, and then you can draw a perfect draw from the other end. So let me just have one graph here. That's the y-axis. It's the x-axis. So that for the sine hyperbolic to look like this. This would be for y1, which is equals to sine hyperbolic of x. And then that is number 1. Number 2, can have 1 for cos hyperbolic. This is the x-axis, y-axis. This is the x-axis. So for the cos hyperbolic, you can be able to see that the y-intercept will be 1. So we're going to have graph like that. So this one here will be 1, where maybe it has cut, where the curve has cut the y-axis, it is 1. And then for the tan, number 3, have a graph for tan, a graph for tan, this being the y-axis, and this being the x-axis. So it will look like it is not surpassing 1, neither -1, so it will look like this. So you can check it's not surpassing -1, and it will not surpass +1. So this one here is y2, which is equals to ch of x, and this one it is y3, which is equals to th of x. So if you can go to the GeoBra, you can see these three curves. You can just plot these three curves on the same graph, you see. Delete that. Then now you can have number 1, you can have y1 is equals to sine hyperbolic of x and see how it look like. That is for the sine. And then you can have maybe y2 is equals to cos hyperbolic x. Here we can see how it look like. And we have now the y3 equals to the tan hyperbolic of x. Again, you can see how it look like. So we can have the three. We have the three graphs here with us. So you can check clearly. You can check them clearly. The red one or the maroon one is for the cos hyperbolic. The blue one is for the tan hyperbolic. And the green one is for the sine hyperbolic. So we'd like now to go to the next step. Now, if you change the period, and maybe you add here, if I add there maybe 5 or maybe 4, you see what is going to change. So when you put, you're going to change the graph depending with the period that we have. So, but in that case, you can have that. Now let us go to the hyperbolic identities. Hyperbolic identities. Can continue to hyperbolic identities. So for the hyperbolic identities, we shall see that there is a cross merging between how we prove the trigonometric identities and how you're going to prove the hyperbolic identities. Now, you can say that for every trigonometric identity, for every trigonometric identity, there is a corresponding, hyperbolic identity. There is a corresponding hyperbolic identity. And it may be proved by either, and it may be proved, by either, number 1, replacing, replacing the SH of x with its definition, exponential x minus exponential negative x over 2, and CH of x with exponential x plus exponential negative x over 2. Or the second way you can prove Roman 2 sorry, the second way you can prove it is by Osborne's rule, by applying or by using Osborne's rule. So for the Osborne's rule, what does it state? It states that that every or every trigonometric identity can be replaced. It can be replaced by the corresponding hyperbolic identity, except where there is a direct or implied product of two signs of two the product of two signs the product of two signs, the sign must change. So that is cosine can be replaced by cos hyperbolic, sine with sine hyperbolic, and tan with tan hyperbolic. But sine squared, for instance, maybe x, will be replaced with negative sine hyperbolic squared of x. So you can see this one, it is positive, so it has become negative. So with that, let us do some examples. We go to questions, for example. Example. Proof the hyperbolic identity. Prove the hyperbolic identity. Prove the hyperbolic identity. CH squared x minus SH squared of x is equals to 1. So let us continue with the proof solution. So we want to apply our first scenario. We have said you can replace CH of x with its definition, exponential x plus exponential negative x over 2, and we have SH of x with exponential x minus exponential negative x over 2. Now, if you substitute here, you're going to have exponential x plus exponential negative x over 2 squared minus exponential x minus exponential negative x over 2 squared. This is what you need to prove to show that it will be equal to 1. So with that, this is the same as to say exponential x plus exponential negative x squared over 4. We can be able to remember a over b raised power c is the same as a raised power c over b raised power c. So you can remember that. So then you can have minus exponential x minus exponential negative x squared over 4. So instead of expanding with the exponentials, we can let exponential x be equal to a and exponential negative x be equal to b. So that our new solution is going to be a plus b squared over 4 minus a minus b squared over 4. So if you expand a plus b, you'll get a squared plus 2ab plus b squared, and this over 4 minus, if you expand a minus b to b, a squared minus 2ab plus b squared, and again this one over 4. So the LCM is 4. The LCM is 4. So and we can have, as you open up the bracket, a squared plus 2ab plus b squared minus a squared plus 2ab minus b squared. So with that, you can put the rectangle together. The a squared and the a squared will go. The b squared and the b squared will go. So we are going to remain with 2ab plus 2ab, which is 4ab over 4. So this 4 and that 4 will go. So I remain with ab. Now ab is equals to what? A is exponential x multiplied by b, which is exponential negative x. So from indices, remember a raised power b times a raised power c is equals to a raised power b plus c. So this means we are going to add the powers, and this will be equal to what? Exponential x plus negative x, which is equals to 0. And any number raised power 0 is equals to 1. The proof ends there. The proof ends there. Now, do you need another example? Let us use the Osborne's rule to prove. Let's go to Osborne's rule. Another example. Prove using Osborne's rule. Proof using Osborne's rule. CH of 2A is equals to CH squared of A minus, instead, yeah, plus SH squared of A. This one is another example. So we do the solution. Now, with Osborne's rule, you only need to know where has this identity from trigonometry has it been derived from? So we can see from this side, from the left-hand side, it might have come from the double angle of, it might have come from double angle of a trigonometric function, that is cos. And so you can see from the trigonometric identity or from the trigonometric ratio, from trigonometric ratio or identity, cos 2 theta is equals to cos squared theta minus sine squared theta, right? Now, from the Osborne, what does it say? It says that a cos or a trigonometric ratio can be substituted or replaced with a corresponding hyperbolic function, except where you have the product of sines. So you can see that Osborne's rule states that Osborne's rule states that trigonometric ratios can be or may be replaced, replaced by their corresponding hyperbolic functions. Hyperbolic functions, but the sign of any direct or implied product of two signs must change. So this means that for the sign So then it means now cos 2 theta will become cos hyperbolic 2a, which is equals to cos hyperbolic squared a. This one here is negative, so it will become positive. So it will be plus sine hyperbolic squared of a. So in short, which is ch of 2a is equals to ch squared of a plus sh squared of a. And that becomes the end of the proof. That becomes the end of the proof. So let us go to the solutions involving hyperbolic functions. So that will land to lesson 2 of our hyperbolic functions. Thank you very much. Thank you for watching Mathematics Solutions. Mathematics made fun. Thank you.